So this lecture is on cement as a building material. We are continuing with our unit 1. Okay, and we have finished with lime, bricks and stones as building material. The next one being cement. Here we are going to cover origin, characteristics, types, maybe the different types and the differences between the types, and some functions or the applications of cement in construction. Now coming to history of cement, cement has been used since probably 12 to 10,000 BC. Okay, and now that cement and what we see today is not exactly same. But cement, meaning of cement is basically something that binds the two building blocks. So that time cement was essentially lime. That's calcium oxide that we studied now in the previous lecture. Okay, and this lime was mixed with volcanic ash. Crushed volcanic ash. This is called pozzolanic. People must have heard of pozzolanic cement. Okay, so lime mixed with this volcanic ash was used as cementitious material. So this was a hydraulic cement which would set under water. Okay, other types of cements used in the history are crushed brick, what we call surki. Okay, crushed tiles, and all these things were used as aggregates. Okay, and a lot of buildings made that time also are still standing. For example, this Pantheon in Rome. This building is still very famous, correct? Now, what we see today, the modern cement that we use today evolved after the Industrial Revolution. After the Industrial Revolution, there was sudden boom in use of cement everywhere in the world. Okay. Now, what is modern day cement? That was created by a Britisher who experimented with heating of limestone and clay until the mixture calcined. Then he started grinding it and mixed it with water. He realized that it is setting very nicely. So then this Portland cement came into existence. Now why it is called Portland cement? Because the stones which were used were from Isle of Portland in UK. Okay. Then next, Mr. Isaac Johnson in 1845, he fired this chalk and clay at little higher temperatures, 1400 to 1500 degrees centigrade. Okay, so then the mixture of clinkers was obtained. This is what is essentially modern day cement. Alright, now coming to introduction. Cement is a substance used for binding and hardening other materials. Water and cement sets and hardens to a chemical reaction called hydration. The process of hardening is described as curing, which requires a particular condition of temperature and humidity. Cement can be mixed with fine aggregates, water to produce mortar, used in masonry construction as bedding, and adhesive to bind and fill the gaps between adjacent blocks of bricks, concrete, and stone. It can also be mixed with water aggregates such as gravel, sand, rock. Okay, just now we studied few more aggregates. What was there? Tile, then broken bricks, right? And sometimes admixtures to form concrete. What are admixtures? Admixtures are the ingredients, the materials that alter the properties of concrete. Okay, it can be used to make renders, screeds, and so on. Ratio of water to cement will determine the overall strength and quality of the mix. The exact property of cement paste are very important. It must be fluid for some time, and after mixing it to allow the mix to be formed into its final shape, so that as soon as you mix water to cement, it should give some time for the mason to pour it in the right formwork. It should not set too fast also. At the same time, it should not be too slow also. It must be then set gain strength so that it binds the aggregates together to produce a strong material. Then the next subtopic is types of cement. Portland cement. So almost all concrete is made with Portland cement. It is also the principal cement used in most masonry mortars and renders. Renders means what is applied on any vertical surface, something like walls and all. Okay? It is renders means now in this context it is basically talking about plasters, what you apply on the walls. It is manufactured by heating together limestone or chalk and clay or shale in large rotary kilns. Chemistry of Portland cement largely consists of calcium silicates which react with water to form a strong and durable cement paste. Okay, then low heat blast furnace Portland cement. This is a special blended cement with low heat of hydration characteristics for mass concreting. Can you give me an example of mass concreting? See what happens, mixing of water with cement is a exothermic process. So when this process takes place, there's a lot of heat produced. So you cannot use very high heat of hydration type of cements in mass concreting because if it's a big bulk, then this heat will require long route to come out to the surface. And more resistance, more the bulk, okay, more are the chances of cracks being formed. Now, a lot of times in 8th semester, the students have been asked which type of cement is supposed to be used for a dam. What are dams? We all know, right? One of the most important structures, right? In every way, in the functionality, in terms of safety, in terms of magnitude, these are huge structures. When you construct a dam, your factors of safety taken for everything, every part of your design is very high. Because slight damage to this dam can bring a catastrophe on the surrounding areas. So when we are going to use cement in construction of these dams, you have to see that the heat produced is very less. Because we don't want even the most finest and hairline cracks to be appearing inside the bulk of dam. By chance the water starts seeping in or any kind of deterioration occurs, then the effects can be on very large scale. So the answer to the question what type of cement is used in construction of dam is low heat cement. What is the answer that our students give is high grade cement. It's not high grade cement in fact. Okay? It is very much low heat cement so that the time taken for hardening can be larger. It can set over a long time. But what is most important is that a heat produced has to be less. Right. The advantage of this kind of cement, let's continue reading. The advantage of this kind of cement over ordinary Portland cement is although it is lower strength gain. See, let me tell you, it's lower strength gain. Okay, it doesn't say less strength. It has high ultimate strength. So eventually it will be strong enough, but only the rate of gaining the strength will be very slow. As well as better workability. Rapid hardening cement will be almost opposite of this. It hardens faster than Portland cement. As it includes more silicates. However, the final strength is only slightly higher, not very high. The strength gain is very fast. In other words, you are constructing something in water. Okay, you want to create a barrier. You can use rapid hardening cement because it will harden very fast. But it doesn't mean it has higher strength. Now, what is the difference between hardening and strength gain? Hardening means it is now that, let's say you want to construct a barricade or barrier, that barrier will be hard enough not to allow water to pass through it. But it will be not strong enough to let something be loaded over it. Are you understanding the difference? Something which is hard will be something that can, have its own shape. It will prevent any water from passing from this side to that side. But if you try to stand over that particular wall, it may not be strong enough. Are you understanding the difference between compressive strength and hardening? Right? So 1 day strength of this cement is equal to 3 day strength of Portland cement. So it is quickly hardened. But at the end of 28 days, both will have hardly any difference. You understand? So with the same water cement ratio, and it is mainly used where formwork has to be removed for reuse. Next is sulfate resisting cement. Sulfate exists in rain and sea water and can be harmful for building material. Okay, when you do this test of durability, in any structures, you test it for this exposure to sulfates and chemicals and all that. Why? Because these sulfates can erode, can deteriorate the structure. Okay, sulfate resistant cement is a type of modified Portland cement that can be used in conditions where concrete is exposed to risk of deterioration due to sulfate attack. So if your structure is somewhere near the industrial areas and all, it is essential that your structure is resistant to all the type of chemical attacks. High alumina cements. Okay, these are also known as calcium aluminate cement, CaC, or aluminous cement. It is composed of calcium aluminates rather than calcium silicates. It is manufactured from limestone, chalk and bauxite. HAC was used in marine applications where it is considered to be resistant to chemical attack, as well as in structural concrete where precast beams. However, HAC is no longer used in structural concrete. Okay, as it is prone to crystalline rearrangement, this can result in reduced strength and vulnerability to chemical attack. Okay, high alumina cement is also used where the temperatures are very high. Okay, in the refractory, somewhere like furnaces and all are being used. You require that cement to be resistant to high temperatures. There also high alumina cements are used. That part is missed out over. Ferrocement is a composite material made up of mortar and light wire of steel mesh. So you will get fibers of steel inside this cement. It's highly versatile form of reinforced concrete. It is considered as RCC, not PCC. Okay. Storage of cement. Okay. Cement. See, it's very important that you keep it away from water, keep it away from moisture. While storing, you don't usually keep it directly on the floor. You keep some wooden beams or bricks and see that the bags are not directly in contact with the floor, right? You have to see the date of manufacturing on the cement bag because it's very important that it is consumed within the time that is prescribed by the manufacturer. If it is not protected in airtight silos or bags on site, it can hydrate. Water initiates hydration process and it can lead to 20% reduction in strength over 3 months and 50% reduction in strength over 2 years. It is important therefore to ensure hydration does not occur. Paper bags of cement incorporate a plastic layer and inhibit moisture intake. We will stop here. I'm at home today, so I don't have a lot of material with me at home. So whatever I could get from the bed, I have used it for this lecture. However, there is one particular difference in type of cement, that is hydraulic and non-hydraulic cement, that is still there. Now that then uses, applications and differences we will cover in the next lecture. So today we are only go through this video, make your own notes. Okay, and last semester also probably I had shared some PPT on cement. You can refer that as well. Alright, bye bye. Hi, so this is the second lecture on cement. Okay, I hope you people have already heard the first lecture. If you have not heard, please listen to the first lecture and then come back to this particular lecture. Right? So now going ahead, let us come to characteristics of cement. What are the characteristics? The first reason why we use cement is because it gives strength to the masonry. Then it is an excellent binding material. What are the other binding materials you all are aware of? Cement is there, and lime also is a very good binding material. In olden days, they used to use some mixture of jaggery and what is urad dal? Urad dal is what you make dosa out of. Okay? Those things were also being used. But in the present day, lime and cement. If you study the books on low cost housing, they even propose using mud and clay as the materials which can be used as binding. But for masonry, I feel the primary ingredient would be lime and cement only. Also, it's easily workable, or in other words, we say it has good plasticity. What do you mean by plasticity? Plasticity or workability, it is measured by a test called slump test. So what is this slump test? You can see this figure that I have just projected. Okay, so you have a cone here. Okay, you pour inside concrete. This gray thing is concrete, and then you tamp it with a rod. Okay, this you can see there is a kind of handle here, black color. You can see this kind of handles here. On that you keep your foot so that the cone doesn't move. When you pour in the concrete and you tamp it, after you tamp it, you slowly lift the cone. Okay, once you lift the cone, see, once it is lifted on top, what will happen? It's a wet concrete, no? It will start flowing down. So, the amount that it has flown down, so you can see now what they have done, they have just inverted the cone. It was at this height earlier. So, the moment cone has been removed, the concrete has moved down. So, the amount that it has moved down is called slump, S-L-U-M-P. Okay, so that slump is measured. Now in this figure you can see the dimensions of this cone. These are standard dimension. Diameter down is 20, height is 30, diameter on top is 10. So you measure it from how much it has gone down from 30. More it has gone down, that means more it is workable, but it should not go right at the bottom. That means it is a complete collapse. Okay, so usually around 100 mm and all is considered good enough workable. 100 to 110 and all is good enough workable. Too much workable means what? How you'll make concrete workable? By adding more water. Now what happens when you add more water? The strength will get disturbed. Okay, strength will be lowered down. So this is called workability in terms of concrete. Now what is giving this workability? How is that concrete made workable? What are the ingredients? Coarse aggregate, fine aggregate, cement and water. Now if you take, let's say if I give you some portion of gravel and sand and I tell you to mix it, would it be easy? Would it be easy? No, these are very heavy things, right? And they are very frictional, they have very high friction value, so it will not be very easy to mix it. So what we do, we add the addition of this cement and water paste makes it easy for you to mold it, to mix it. Okay, so cement also adds to workability of the concrete. Of course, that is not a prime reason why it is added, but yes, it adds to the workability. Prime reason is binding and imparting strength, obviously. Right? Now going back to our presentation, the next characteristic is it also offers good resistance to moisture. We do not want to use building materials which are going to pull in the moisture, because I told you moisture largely affects its durability and its strength. Both the things which are of prime importance as a building material or engineering building material is it should be having good strength, and secondly it should be durable. What is durable? I have been telling you this thing again and again. Durable means in the long run, down the 10 years lane, it should be still be used. You're not supposed to keep replacing the building material every now and then. Right. Let's go to the next slide, requirements of good cement. So it should first possess a uniform color. It should be free from lumps. What does it indicate if there are lumps in the cement? That means it has already pulled in moisture. And I told you, the moment it pulls in moisture, the strength can go down from 30 to even 50%. Right? It should be smooth, as it should get sunk completely if thrown in water. Okay? The ratio of percentage of alumina to that of iron oxide should not be 0.66. Now, what is this alumina and iron oxide? These are some constituents, ingredients present in cement. Okay, and they impart certain particular property. I will come to it in the further part of the presentation. But yes, their ratio should not be less than 0.66 in cement. Total sulfur content should not be greater than 2.75. Okay, see what happens, certain ingredients, no, when they are more, it can make the cement unsound. So when you have sulfur, okay, it is obviously used, it is useful in making good sound cement, but in very small percentages. If it is in excess, the same cement can become unsound. What do you mean by unsound? It can expand, it can disintegrate when it is in the form of mortar or in the form of concrete. If there is too much of certain compounds like sulfur, then the concrete or mortar can disintegrate. Magnesia should not be more than 5% in weight. Okay, for the similar reasons. Okay, if magnesia also is in high percentage, more than 5%, that also can make cement unsound. Unsound is a technical word. Okay, it means it might expand. Unsound material means something which will expand or something which can disintegrate, right? Then insoluble residue in cement should not exceed 1.5% by weight. When heated, cement should not lose its weight more than 4%. Okay? The specific surface of cement as from the fineness test should not be less than 2250 millimeter square per gram. What does the specific surface indicate? It just indicates how powdery, how fine the cement is. More fine, better it is. That's why they say it should not be less than. It can be more than. You can still make it more powdery, but it should not be less than. So it's basically limiting the fineness. It is giving you how much granular, what is the maximum permissible granular texture that the cement can possess. Okay. Initial setting time should be about 30 minutes and final should be about 10 hours. Cement should not expand more than 10 mm in soundness test. Now, what is this soundness test? And okay, I'll just show you what is soundness test. Yeah, so you can see the apparatus for test for soundness. Okay, this apparatus is called Le Chatelier's apparatus. Okay, it's like a cylinder, and then there are two projected needles, kind of a thing. Okay, this is then what you do, you fill this cylinder with the cement and water paste. Okay, here it is a systematic diagram. See, it's 30 mm in height. Okay, and then you can see these two needles, they are exactly parallel. So what basically this apparatus is doing, it is measuring the change in the volume. So once you pour the cement water paste in this and then it hardens, once it hardens, you have to check whether these needles have deflected. Meaning the distance between these needles when the cement was in a wet state and after the cement has hardened, whether the initial distance difference and the final difference is same. So basically what you are doing is you are measuring the volume change. So I don't want to go into depth of this test. I will just tell you, okay. So let's look quickly at the procedure. So what is done is you oil the mold, okay, and then fill it with the cement paste formed by gauging cement with 0.78 times the water required to give paste of standard consistency. Now again, standard consistency, what it is. Okay, let's keep this part away. You people all just need to know that you have to make a cement and water paste. Once that is done, Then you measure the distance separating the indicator pointers to the nearest 0.5 mm. So you note it down very accurately using vernier caliper. Okay. And then after that you keep this entire assembly in a boiling water bath. Okay. It to around 25 to 30 minutes. And you keep it for around 3 hours. Once that is done, then you find out the distance between the indicators again. Now this difference between the two measurements, first that you took before when the cement was in wet state, when it was just poured, and later on after boiling it for around 30 minutes, right? You note down the difference, and that should not exceed 10 mm for ordinary cement and rapid hardening cement and low heat Portland cement. Okay. So in case what happens if this is more than 10 mm, then it is said to be unsound. Okay. So you know what is the meaning of this word soundness. So if you get that expansion more than 10 mm, then the cement, if used in mortar or if used in concrete, can have expansion or disintegration in future. Right. Now going ahead, the first ingredient in cement is lime, written as CaO, calcium oxide, or it is also in the form of calcium hydroxide. The presence of lime in sufficient quantity is required to form silicates and aluminates of calcium. Deficiency in lime reduces the strength property to cement. Please excuse my typographicals. Deficiency can cause cement to set very quickly. Excess can make it unsound. Again the word comes. The excessive presence of lime can cause cement to expand and disintegrate. The next one is magnesia. It's present in the form of magnesium oxide. Chemical formula MgO. Now this ingredient, if it is present in very small amounts, then it imparts hardness and color to cement. Okay. And high content of magnesia again will cause the cement to become unsound. So magnesia should not be present more than 2%. Okay. Next is iron oxide. Iron oxide is written as Fe2O3. Okay. Again, this ingredient also imparts color, but it also adds to hardness and strength to the cement. Okay. At very high temperature, it imparts or it participates into a chemical reaction with calcium and aluminum to form tricalcium aluminoferrite. Okay. Tricalcium aluminoferrite imparts hardness and strength to cement. Okay, these terms are right now new, and you may find that I am speaking something in Greek. But you guys have to know this very well. These terms are going to be your future. Okay. So you guys have to remember what is tricalcium aluminoferrite, what is tricalcium silicates, dicalcium silicates, what is the meaning and why they are present in cement and why do we need them or how much do we need them. So get used to these things, okay? Right, going ahead, calcium sulfate, CaSO4. This ingredient is in the form of gypsum. You people have heard this word gypsum. And its function is to increase the initial setting time. It increases the initial setting time of the cement. Next is sulfur trioxide. Its chemical formula is SO3. It should not be present more than 2%. Now this time, now I'm not going to tell why not more than that, because it makes it unsound. And the last one is alkalis. These should not be present more than 1% because it can cause efflorescence. Okay, but it usually these alkalis fly off when the cement actually gets heated in the process of manufacturing. But they should not be more than 1%. Going ahead, this will be our third video on cement as building material. Right, so we have already covered the functions of all the ingredients that are present in cement. the next are these two ingredients which are displayed on the slides. These are the harmful ones. We do not want them in larger quantity. The first one being alkali oxide. If you have more than 1% of alkali oxide in the cement that you are using for concrete, then there are chances that your concrete will eventually fail. Okay, it can cause a lot of disintegration in the concrete. Similarly, if you have more than 5% of magnesium oxide in the mortar, that mortar can crack or expand while it starts setting. Okay, now coming to what is the meaning of setting. Okay, so setting action starts as soon as you add water in the cement. Okay, ingredients of cement will chemically react with water, and this in the process of setting, in the process of hardening, there are different compounds, chemical compounds, which will be formed. Okay, now formation of these compounds is not simultaneous. It is at different time, different compounds will be formed. Okay, but the setting action of cement will continue for a long time. Okay, final setting can even be achieved at the end of an year. The final strength gain, I mean, can be achieved even at the end of a year. The mixing of cement and water results in a sticky paste. Okay, this paste will go on gradually thickening till the cement hardens and it gives you a rock-like structure. It is found that in ordinary cement, around 70% of its final strength will be achieved at the end of 28 days. That is the reason we do the test at 28 days. Compressive test on cement or compressive test on concrete block is done at the end of 28 days, because at that point around approximately a rounded up figure of 70% of its final strength can be achieved. So once you know at the 28 days particular strength, then you can calculate what will be its final strength, and they say around 90% of the final strength will be around after 1 year or so. Right, now let's come to the chemical compounds which are responsible for this setting. Right, the first one is tricalcium aluminate. It's written as 3CaO Al2. This is small l, okay, not capital L. Al2O3. Okay, this compound is formed soon after the water is added. Similarly, excuse my typographical. Similarly, second one, tricalcium aluminoferrate. This is also formed as soon as the water is added. So basically, these two compounds are formed somewhere after 24 hours. Okay. Whereas tricalcium silicates and dicalcium silicates, when it comes to tricalcium silicate, it is formed somewhere within a week. Okay, so at the moment you add water, within a week, tricalcium silicates are expected to be formed. And it is mainly responsible for imparting the strength over the period of setting. Okay, dicalcium silicate, sorry. This compound is formed very slowly. Okay, the progression is very slow. Okay, and you can see from the graph, okay, the x-axis is representing age in days and the compressive strength is on the y-axis. Now, these two are tricalcium silicates. Okay, this is C3A is tricalcium aluminate, and C4AF is tetracalcium aluminoferrate. Now you can see as the days are progressing, there is not much of strength gain for when it comes to the first two compounds. Whereas for tricalcium silicates and dicalcium silicates, the strength gain is enormous as the days progress. Okay, so I want to show you something which is there available on the net. Okay, now tricalcium silicates, they are usually written as C3S, and this is supposed to be dicalcium. Okay, dicalcium silicate is written as C2S, and their chemical formula is 3CaOSiO2 and 2CaOSiO2. Okay, Two silicates, namely tricalcium and dicalcium silicates, control most of the strength giving properties. Upon hydration, both C3S and C2S give same product called calcium silicate hydrate and calcium hydroxide. Tricalcium silicate C3S giving a faster rate of reaction accompanied by greater heat evolution. So, in the process of hardening, it is liberating a lot of heat and it develops early strength. Okay. On the other hand, dicalcium silicate hydrates and hardens slowly. Okay. Provides much of ultimate strength. So, the strength gained in the later stages of your concrete, okay, in its little older age will be due to dicalcium silicate. In its younger age, it will be due to tricalcium silicate. It is likely that both C3S and C2S phases contribute equally to ultimate strength of cement as can be seen in the figure 1. Okay, and you see these two are mainly contributing to the strength. These two aluminates and aluminum ferrite, these people are not actually major contributors to the strength. Tricalcium silicate and dicalcium silicates need approximately 24 to 21% of water by weight. So, whatever water you are going to add in the concrete or mortar, 24 to 21% of it is going to be consumed by these two compounds alone, okay, for the chemical reaction. But C3S liberates nearly 3 times as much calcium hydroxide chemical reaction as compared to C2S. However, C2S provides more resistance to chemical attack. That is why higher percentages of C3S result in rapid hardening with a early gain in strength at a higher heat of hydration. On the other hand, a higher percentage of C2S results in slow hardening, less heat of hydration, and greater resistance to chemical attack. C2S is responsible for concrete strength beyond 7 days of age. Now, tricalcium aluminate and tetracalcium aluminoferrite, they are written as, tricalcium aluminate will be written as C3A and tetracalcium aluminoferrite will be written as C4AF. You have to get used to these acronyms or the ways to depict these compounds, okay, because their chemical equations are a little complicated. Okay. The compound C3A is characteristically fast reacting with water and may lead to immediate stiffening of the paste. Okay, this process is called flash set. You do not want the cement grout, cement water, wherever it may be, in concrete or mortar, to set immediately. You don't want the flash set. That is why gypsum is added in the cement. Why? It is to prevent such fast reaction. C3A reacts with 40% of the water by mass. Whatever water you have added, 40% of it reacts with C3A. But C3A itself is in very small proportions in your cement. So, this is more than required for silicates. Okay. Your C2S and C3S requires much lesser. How much we say? 21 to 24%. But C3A requires 40%. However, since the amount of C3A itself is very small in the cement, the net quantity required for hydration will not be affected. Okay, what they are trying to say is, if too much of C3A is there, then since they are consuming major portion of the water, C2S and C3S, okay, tricalcium and dicalcium silicates, which are responsible for strength, obviously you want them to get water, right? Because they are going to give you strength. But the percentage of this compound is very less in cement. So, although it is consuming a lot of water, it being in very small quantities, not much volume of water will go to it. Okay. So, the net water required for hydration of cement will not be subsequently affected. It provides weak resistance against sulfate attack and its contribution to development of cement strength is perhaps less significant. Okay. Tetracalcium aluminoferrite hydrates rapidly but contributes little to concrete strength. Majority of Portland cement is because of C4AF. Hi, so continuing with the last topic, cement. This lecture we are going to discuss what are the different types of cements available. Okay, the first classification is natural and artificial cement. So what is natural cement and what is artificial cement? Natural cement is obtained from stones, okay, by burning and crushing the stone. Now these stones should contain clay, should contain carbonates, right, lime and carbonates of magnesia, okay. These will have a typical brown color, and as soon as you add water to it, it should start setting. Now primarily these natural cements will not be as strong as the artificial cement. So can you give me an example of natural cement? Yeah, we've already studied the material. It's lime, okay, obtained from limestone, sometimes from shale and other different types of materials, sometimes from normal stones that you get, okay. Obviously, based on the source, the purity of the lime or the quality of the lime will change, right? But lime is a natural cement. Now, the cement that you guys or we use in today's day is an artificial cement. It is obtained by burning calcareous and argillaceous material at very high temperatures. So, what is calcareous? Calcareous is something which has calcium, right? And argillaceous? Argillaceous means something which has clay. Okay, clay is the material that's going to hold the things together, the binding property, right? The calcined product of these materials is called clinkers. Calcined means burnt at very high temperature. Okay. Small amount of gypsum is also added. Why is gypsum added? To slow down the setting, right? You don't want it to be flash set. You don't want it to be set very fast. So sometimes gypsum is added. And then pulverized into cement. Pulverized means broken to very fine powder. More finer, better is the setting, right? The next subtopic is hydraulic cements and non-hydraulic cements. Now, what are hydraulic cements? Which will be hardened by hydration in presence of water. Limestone, clays and gypsum are the main raw materials which produce the hydraulic cements. These raw materials are burnt at very high temperatures to manufacture hydraulic cements. Okay. It's a cement that not only hardens by reacting with water but also forms a water resistant product, right? So it's a very moisture resistant product. That's why we use it in rendering, in application over the surfaces, correct? Produced by pulverizing clinkers, which consist essentially of hydraulic calcium silicates, usually containing one or more of the forms of calcium sulfate as a interground addition. Okay. Then non-hydraulic cements do not require water to get hardened. It gets hardened with the help of carbon dioxide, sorry. This type of cement needs dry conditions to harden, which is the example, classic example is lime. Okay, lime, gypsum plasters and oxchlorides are required raw material to produce non-hydraulic cement. Okay, slaked lime is a non-hydraulic cement. Now going to varieties of cements which are available in the market. These are various varieties of cements which are available in the market. Acid resistance, you have blast furnace cement, you have colored cement, expanding cement, high alumina cement, hydrophobic cement, low heat cement, pozzolana cement, quick setting cement, rapid hardening cement, sulfate resistant cement and white cement. Let's learn these things in detail. As the name suggests, acid resistant cement will be obviously acid resistant to all the acids. Okay, now when I say resistant to all the acids, in not very strong forms, okay, diluted acids which they are resistant to. Now, what are the materials which are required to make the cement acid resistant? It's quartzite and quartz. Okay, what is quartz and quartzite? Actually, quartz is a mineral and quartzite is a stone, so it doesn't really make much of a difference. Only thing is, quartz can be uh, obtained from various different stones also. Okay, but primarily when I'm talking about acid resistant cement, the stone which is used to make this aggregates is quartzite only. Let's remove this. Let's not create any confusion. Okay, right. Now, other additives are sodium fluorosilicate, an aqueous solution of sodium silicate or soluble glass. Okay, this is used for making the cement acid resistant. Now, when you have these industries, okay, which are dealing with a lot of chemicals, let's say, for example, fertilizers or pharmaceutical companies, okay, in such places, all the coatings and installations have to be acid resistant. So, in such cases, we use this type of cements. Okay, by addition of 0.5% linseed oil and 2% salicylate. Now, salicylate is a kind of admixture, okay. You can make the same cement acid and water resistant also. Right, now going to the next type of cement, blast furnace cement. Here the slag is obtained from blast furnace. Okay, now this slag is a byproduct in manufacturing of pig iron. Okay, and its basic elements of this particular cement is alumina, lime, and silica. Okay, now clinkers here of the cement are ground to about 60 to 65% of slag. Okay, more or less the properties are similar to ordinary cement. Okay, it has early strength. It has a less early strength and requires way longer curing period. Okay, so it will gain strength eventually, but you will have to cure it for longer time. Okay, it is very durable, but it is not suitable for arid zones. What do you mean by arid zones? Arid areas? Arid areas are the places where the moisture content or humidity is very less. In such cases, this kind of cement is not suitable. The next one is colored cement. So in colored cements, what we do is we add certain percentages of pigments. Okay, around 5 to 10% pigment is added. More than 10% is not suitable because the strength gets affected. Okay, so chromium oxide pigment, this one, the green one that you can see. Okay, this will add green color. For blue color, you add cobalt. Iron oxide pigments are in various colors. Okay, so based on their concentration and type of pigment being used, these are all iron oxide pigments. I have not titled this, but okay, fine, because you know the various pigments will be various colors. So your colors also will go from brown, red to even yellow. Okay, manganese dioxide, I couldn't get the pigment, but can you see this? These are different colors of mangalore tiles. Manganese dioxide gives black to brown color and they are widely used in tiles. Okay, then these kind of cements are used in floor finishing. You want a particular floor color, and while joining the tiles, you don't want a typical gray color in between that line. If you don't want to see, you can use this kind of cements so that the joints between the tiles or anything looks seamless. Okay, they are also used in external surfaces. Then the next type of cement is expanding cement. Addition of expanding mediums like sulfur aluminates and stabilizing agents make the cement expanding type. Okay, usually cements shrink on the on hardening or while setting, whereas this is the type of cement which will expand on hardening. So that is why it is used when you need water tightness. You don't want shrinking. If there is shrinking of the member, then there will be gaps created. So you don't want that kind of cement. So when it is directly in adjacent to any kind of water bearing member, then this type of cements can be used. Alright, next is high alumina cement. This is produced by grinding clinkers of bauxite and lime. The total alumina content should not be less than 32%. Approximately, usually it is around 40%. Okay, and ratio by weight of alumina to lime should be in the range of 0.85 to 1.3. Okay, the advantages of this type of cement is the initial setting time is around 3.5 hours, while the final setting time is around 5 hours. So therefore what happens, it allows for time for you to mix and place. Okay, there's no hurry. Okay, it's giving you sufficient time. Then it can stand very high temperatures. It evolves great heat during setting. That's why it is not affected in frost areas. So areas where there is a lot of icing or there is a lot of snowfall, you can use this particular type of cement. Okay. It has better resistance to acids. Okay, it sets very quickly. Okay, and attains ultimate strength also very quickly. Right? Its setting action mostly depends on the chemical reactions. Hence, you need not grind it to very fine powder. Otherwise, I have told you, more pulverized, better is the cement. But here in case, the setting is largely due to the chemical reaction, not because of the physical reaction so the pulverizing is not really important in this case. Of course, you need to pulverize it, but don't require it to very fine particle sizes, right? Then the disadvantages of this cement, extreme care has to be taken to see that it does not come in contact with even slightest of lime or ordinary cement. Okay, it cannot be used for mass construction. Why? Because it involves a lot of heat. So if you're going to use it for mass construction, then there are obviously going to be cracks seen on the surfaces, and it's a very costly type of cement. The next one is hydrophobic cement. This cement will contain admixtures which will decrease the wetting ability of cement grains. Okay, the usual hydrophobic admixtures are acidol, naphthalene soap, oxidized petroleum, and these substances will form a film around the cement grains. Okay, but even though there are these films which are around the cement grains, the moment you add water, the setting will start. So it's not really affecting the setting. Only thing, it may just slow down the strength gain. So the initial strength gain is little less. But at the end of 28 days, it will be same as ordinary Portland cement. When hydrophobic cement is used, fine pores in concrete are uniformly distributed, and thus the frost resistance and water resistance to such concrete is considerably increased. Okay, then the next type of cement is low heat cement. As the name suggests, it will have low heat of hydration, and that's why it makes it ideal for mass concrete. Can you give me an example of what mass concrete structures where there is mass concreting happening? The primary one is dams. Okay, I probably have mentioned this before. So in case of dams and all, you need cements which are having very low heat of hydration. Okay, when maximum temperatures achieved must be controlled in order to reduce the risk of thermal cracking. Okay, now this has what is this C3A? Tricalcium aluminate is around 5%, and dicalcium silicate is around 46%. In normal cement, I have purposely put this note. This note in red is not pertaining to low heat cement. Just to tell you, in a typical cement, you have tricalcium aluminates around 5 to 15%. So you can see in low heat of hydration, you are keeping it to the lowest permissible value, lowest possible value. Why? We do not want sudden flash heating or sudden heat. You see, this particular component is responsible for giving out heat, so you need to limit it. And you need these dicalcium and tricalcium silicates for strength gain. So you keep this to around higher value. Which one? Dicalcium silicate. Understood? Which is otherwise around 15 to 30%. You In this particular type of cement, you will get it to around 46%. Okay, it will usually exhibit lesser compressive strength as compared to Portland cement, and initial setting time for this is around 1 hour, while the final setting time is around 10 hours.